This is linear substitution. So we actually kind of do use linear substitution in methods, but it's just not, we aren't actually taught it. We're just kind of given the formulas um, that use linear substitution. So all the formulas that we're given about if you're integrating um, a function, say like e to the power of 2x, we would use linear substitution to actually get these answers in Specialist, but in methods we're just kind of taught the formula. So this is kind of, yeah, like the method behind getting those formulas, really. Um, so we use linear substitution when we have a linear component within another function. So within another function means that the linear component is something that we can't integrate directly. Or in other words, it would be something that we could integrate directly if it didn't have a linear function there. If it just had an x there, we would be able to integrate it. So in these two examples here, we have the integral of 1 over root 3x plus 1 with respect to x, and the integral of 1 plus x squared with respect to x. So for both of these examples, we have a linear component, 1 plus x, 3x plus 1, but they are within another function because we can't integrate these straight away using the rules in our formula sheet. However, if these two examples contained not a linear component, but like just an x, if we had 1 over root x, we would be able to integrate that just by using the power rule. Similarly, with this one, if we just had x squared instead of the linear component, we would be able to integrate it. So my point here is that if you have, or if you've been asked to find the integral of a function, and like within that function, instead of just having an x, you have a linear component, it means you need to use linear substitution. So the steps for using linear substitution is firstly to let the linear component equal u. Now you don't actually have to let it equal u specifically, it just needs to be like any letter that you're treating as like the substitution, but I just typically tend to use u. Once we've done that, we are going to derive u with respect to x, as in find du dx, and then we are going to isolate dx. So don't worry if you're getting too mixed up with these right now, we are going to go over a few examples. The third step is to sub u and dx into your original integral and integrate with respect to u. And what we mean by integrate with respect to u, if you're unfamiliar with the language, is that it means we're just going to integrate normally, but like instead of x being the variable, u is going to be the variable. And we'll go over an example of this again in a second. And then once we've done that, we're going to sub our linear component back in for u. And then we're going to be left with an integral in terms of x using our linear substitution. So down here, I have some tips for complex questions. These are more so for like the more higher achievers or the people who are looking for some extension work. These are just some of the notes that I had for linear substitution when I was in year 12. So, I mean, I guess directly from the horse's mouth kind of thing. I will go over these in a second. We're going to do the example first, and then I'll explain these tips in detail, just so that you guys get like a deeper understanding of what we're actually doing, and then we'll go over the tips. So, in our example here, we need to find the integral of 1 on root 3x plus 1. So, The first step when you're doing any kind of integration is to recognize what method you need to use. If it helps, you might actually want to like write down a list of all the methods when you're learning, just so you don't like forget any of them. Once you've practiced enough, they'll kind of like come to you more intuitively, but just when you're learning, it might be helpful. So yeah, right here we have 1 over root 3x plus 1. We have a linear component within another function. We can't integrate this just kind of like normally using any of the formulas in our formula book. So we're going to have to use linear substitution. So having identified that we need to use linear substitution, remember our first step is to let u equal the linear component. So the linear component is 3x plus 1. So we're going to let u equal 3x plus 1. So again, first step, let u equal the linear component. If it does help as well, you can like copy paste the instructions for each of these integration methods into your notes or something like that from the slides that are downloadable. That might help you learn them as well. Okay, our second step is to find the derivative of u with respect to x. And by that I mean find du dx. Now, you could write this as just u dash, but I wouldn't recommend it because we're actually going to be manipulating these du dx's as we have in the instructions. So the derivative of u with respect to x is just 3. And remember, what we need to do from here is actually isolate the dx. So we're actually going to be splitting this du and dx up. And once we actually complete the rest of the integral, why we do this will become more apparent, and I'll go over that when we get to it. I know when I first learned this and I kind of saw that we were like separating the du and the dx, I was just kind of like a little bit surprised. I was like, wow, I didn't even realize that those could be separated. It kind of seemed like they were like a package deal to me. But I guess in Specialist, you kind of get used to thinking outside of the box a little bit. And like more things than you think are actually possible, which is kind of fun. But yeah, so we're going to separate and isolate the dx. So we're just going to take that 3 down the bottom. And now we're going to be getting onto our next step, which was to sub u and dx into our original integral. So we're going to substitute u equals 3x plus 1 and dx equals du on 3 into our original integral. So we're going to have 1 over root u multiplied by du on 3. And then once we've done this, we now need to integrate with respect to u. So we're going to be acting as if u is the variable instead of x. Now, as you can see, what we've done here is by doing this linear substitution and by kind of like subbing dx in terms of du, we now have something that we can integrate. So the purpose of doing this stuff with du dx is so that we had something in terms of du that we could put back in place of dx, allowing us to actually integrate. Because if we had left the dx here and, you know, we just had, instead, we just had by dx and we didn't have this du, we wouldn't be able to integrate it because we have one variable being u and one variable being x. We need to actually have this this end part being in terms of the same variable that we're integrating with respect to. And we will get into a few more examples later in the lecture where this becomes a little bit more tricky and frustrating. But for now, what we can do is integrate. So we can take this third out the front. We know that this is going to be the integral of u to the negative half because we're using our index laws. So anything square root is to the power of half. We can move that up the top and get it to the negative power. If you're struggling with any of this like simple integration stuff that we'll be going through, I'd recommend having a look through the Year 12 Methods lecture that should also be available during the April lecture series, because we go through more of this stuff then, because it's more of the stuff we learn in methods. And now to find this integral, we're going to have a third multiplied by 1 divided by 1/2 u to the half plus c, which is going to give us 2 root u on 3 plus c. And remember, our fourth step is to sub our linear component back in for u, because then that gives us our integral back in terms of x, which is exactly what we want. So we're going to have 2 root 3x plus 1 over 3 plus c. And that is going to be our integral. Okay, so this was a pretty simple example. Typically with linear substitution in isolation, without any other methods, it doesn't really get too much harder than this. But we will go over a few of the complex tips that I had for you guys, just if you're looking for some extensions. If you just kind of are new to this linear substitution stuff, and you're already feeling a little bit boggled, maybe save these tips for later. They might boggle you a little bit more. They are useful for when you're getting into the trickier questions. So the first tip that I had is, if you have a linear component and an extra x, such as in this question here, where we have the integral of x on root 3x plus 1. So it's exactly the same as the one we had up here, except instead of the 1 up the top, we actually have an extra x. So we kind of have, instead of just one linear component, we have like 2 linear components that we're working with that are different. 2 different linear components. So if we only follow the above steps, we would be trying to integrate with respect to u, but we would have an extra x, because instead of just having the 1 up the top, when we are integrating, we would actually have x on root u du on 3, and we would then have like an x and a u and a du in all in the same situation, and then we wouldn't be able to integrate because we have this mixture of variables. So what you need to do for these questions is, once you let the linear component equal u, you need to rearrange this expression in terms of u and sub this back in again. And this way, in your integral, you're only going to be left with x. You're going to, with what, u, sorry. You're going to eliminate all of the x's. So what I mean by this is that you would have your u equals 3x plus 1, and then you'd rearrange this to get x equals a third u take 1, and you would sub this in for the x up the top here. And then in your integral, you would only have it in terms of u, and then you would be able to simplify it a bit using algebra and integrate from there. So then you need to, as I said, sub this back into your integral, and now you have an integral only in terms of u. So the takeaway from here is, if you're asked to integrate something and you have a linear component and an extra x, or in other words, you have 2 different linear components, what you can try to do is rearrange your substitution u equals the linear component, rearrange that to isolate x, and then sub that in. Because what that allows you to do, especially when your extra x is on the numerator, is that allows you to just split up the fraction and integrate really easily. If you feel like maybe you've seen that a similar question before or something like that, I'd recommend just like going through this question, following these steps to better understand it, instead of just kind of like writing down the procedure. Okay,